It's a great pleasure for me to introduce Professor Zhi-Hua Zhou from Nanjing University in China. He is the founding director of the well-known Lambda Lab at Nanjing. He's also dean of the School of AI and head of the Department of Computer Science. He has been one of the very first researchers in China to go for the field of machine learning, and he has had a profound influence on the field. He's been extremely active in organizing a lot of conferences and events. He's chaired HCAI, AAAI, ICDM, the Chinese AI conference. He's a fellow of the ACM, the AAAI, AAAS, IEEE, and many more organizations. He's written various books. Most recently, he's introduced a book on machine learning that has just been translated, and that has already sold 200,000 copies in China. His research field is how to enable computing machines to handle ambiguity, and he's well known for the work on multi-instance, multi-label, multi-view, and semi-supervised learning. And he also has a traditional interest in the combination of learning and reasoning, which he will also address today. From his website, I take the quote that research is for fun, and I'm sure his talk is going to be both fun and very inspiring. So let us welcome Professor Zhi-Hua Zhou.
Thank you, Luke, for the generous introduction. And I want to thank Nichols and all the other organizers for inviting me here. So first, may I share my screen? Hi, Nichols. May I share my screen?
It's the green button underneath. Do you see it? There's a button over there. Share screen.
Okay. Can you see my screen now?
Yes, we do. Thank you.
Okay. So hello everyone. Today I want to share with you. The title is Leveraging Unlabeled Data from Pure Learning to Learning plus Reasoning. So as we all know that current machine learning techniques seriously rely on huge amount of labeled data. Well, we all know that in many practical applications, although it's very easy for us to collect a huge amount of unlabeled data, it's generally difficult to obtain the labels because it requires human effort. For example, if we want to know the label of the web page, we need to require a user to read the web page. Well, on the internet, there are almost infinite number of web pages, so it's impossible to have a user to read all the web page. So they are remained unlabeled. If we can only use labeled information to train the model, then this unlabeled information will be wasted. So the key is to try to use unlabeled data together with labeled data to improve the performance of machine learning. So this is not a new area. So my talk will contain two parts. In the first part, I will quickly give you an overview of how the machine learning community have tried to use unlabeled data. They are all pure machine learning approach. Then I will spend half of my time to present a recent advance which tries to combine machine learning together with logical reasoning to use unlabeled data. Also, it's possible to do some other things such as knowledge refinement and so on. So let me come back to the topic of to use unlabeled data. A very simple idea come to our mind is to do self-training or self-learning. For example, if I just have some labeled data, from the labeled data, I can train a model. This is a classifier or a learner. Then I can use a learner to make prediction on the unlabeled data. In this way, I can get more labeled data, although the labels are given by the learner itself. So we can understand that many self-labels are incorrect. So this is a dirty or noisily labeled data. Anyway, we can use the labeled data together with the original labeled data to train the learner. So this is a very basic idea of self-training or self-learning. So we can see the key is to explore the pseudo labels. So it will seriously suffer from the incorrect pseudo labels. Then how to improve this? The idea is actually very simple. Based on the self-labeled data, we can introduce some mechanisms such as data editing, we can check or examine whether the label data is very likely to be incorrect or not. If we examine that and found it's very easy to be noisily infected, then we can try to revise the label or fix the data. In this way, we can get a cleaned self-labeled data. Then the learned model can be improved because more cleaned data can be used. Though the data editing approach has introduced many mechanisms such as the statistical hypothesis testing, but most of them are still heuristic. So what we want to require is, do we have more principled way to leverage unlabeled data? So there are several general ways. The first general way is active learning. Now, because we only have labeled data very small, and then we could not have a very good model, but we have a huge amount of unlabeled instance, then we can assume that we can get the help of an oracle. This is actually a human expert or human annotate to help us to label some unlabeled instance. Of course, we could not require the oracle to label all the instances. So the key or the goal of active learning is just to try to query as few instances as possible to train an accurate model. So briefly speaking, during the past 2 decades, there are many machine learning approaches have been developed. Roughly speaking, we can categorize them into 2 classes. The first class, just to try to query informative instances. For example, we can train a subvector machine based on the label data. Then we know the instance very close to the separator, we're very close to the board, will be less confident, and they are very likely to be something that are mistake. So we can select them as informative ones for query. So this is a very simple idea. Another category of approach is just to try to query representative instances. For example, we can divide the whole data set into several groups. Then from each group, we can identify some representative ones to ask the human expert to give the labels. But the first category of approach generally suffer from the fact that because we only have a very small number of label data, then based on the limited label data, you can only have a very poor model. Then based on the poor model, it's very difficult for us to have a reliable estimation on what instance is informative. Well, the second class of approach also suffers on the quality of the finding of the representative list. A general approach is try to do some clustering, but if you have a very excellent clustering result, then you can identify some good candidates. But if the clustering quality is not that good, then the performance will be not so good. A recent attempt is just to try to combine both. For example, we can query informative as well as representative instance together. The basic idea is first we calculate one score based on the informativeness and another score based on the representativeness. Then we combine both scores together to get a total score. Then we rank all the unlabeled instance according to the total score and pick the top ones to query. So this is a very basic methodology, and many active learning algorithms have been developed based on this idea. But the key of active learning is human in the loop, because we always assume there are human experts which can be requested to help us to label unlabeled data. Then what can we do if there's no human in the loop? So the idea is to go to the help for semi-supervised learning. So before I give an introduction on semi-supervised learning, we need to understand why unlabeled data can be helpful. Because now what we want to build is a supervised model, and the label information will be crucial. But the unlabeled data does not have label information, then why it can be helpful? In active learning, this is very simple because the human expert provides additional information about the labels, so that will be helpful. But semi-supervised learning assumes that there's no human intervene, then why unlabeled data still can be helpful? So here I give a very simple explanation. Now suppose the data is well modeled by a mixture of density in this way. We have capital L number of mixture components, and each component is characterized by the parameter theta and combined with a coefficient alpha. Then based on this very simple model, the optimal classification rule is the max posterior rule. written in this way. So we can see at the right-hand side of the equation, there are two terms. The first term means once we observe the instance xi, and if we know it's generated from the JS component, then how about the probability of this instance is with a class k? So to have an estimation on this term, we need to have label information. But for the second term, it reads that if we observe the instance xi, and how about the probability that this instance is generated from the JS component? So we can see this term does not involve any label information. So we can use unlabeled data to help estimate this term. With more unlabeled data, we can expect that the estimation on this term may become more reliable, then the whole prediction can be improved. So this is a basic idea about why unlabeled data can be helpful. So if this explanation was not that intuitive, here is a more intuitive explanation. Now suppose we have just two data points, one is blue, one is red. Then these are two labeled data. Then if we want to make a model to predict the middle one, whether it's blue or red, because the white point falling exactly in the middle of these two labeled points, then what we can do is random guess with 50% accuracy. But now, if we do not allow to observe more labeled data, but we allow to observe more unlabeled data, for example, the grid points, even though we do not know their labels, once we observe this unlabeled data, we can have a higher confidence to conclude that the middle point should be blue. So this is because unlabeled data disclose some label information because they are from the IID distribution. They are IID sample together with labeled data. So the distribution are the same. So during the past 2 decades, there are many approaches developed for semi-space learning. So roughly speaking, there are 4 categories of approach. The first category is generative methods. In this kind of approach, we use a generative model for the classifier, and then we can employ the EM approach to model the label estimation or parameter estimation. For example, the previous explanation I show you based on the mixture of experts is a kind of generative methods. But for this kind of methods, in practice, generally, we need to make a right assumption. Because if we make an incorrect assumption about the model, then with more unlabeled data, the performance may be even degenerated. But how to get a right assumption of the model may have to get help from the domain knowledge. The second category approach is an extension of the famous soft-vector machine. So here, we just try to use unlabeled data to adjust the decision boundary such that the final decision boundary will go through the low density region. For example, suppose now we have only 3 labeled data and they fall into 2 classes, then the large margin separator will be the dashed line. Now suppose we have many unlabeled data, just the grid points, then what we want to identify, the separator should be the one which go across the low density area. Then in order to identify this separator, we need to consider all the possible label assignment of each data point. Then this approach will lead to a large scale optimization task. So the main focus of this thread of this line of research just to focus on how to effectively address the large scale optimization task. And the third category of approach is graph-based methods. Because given a data set, we can map it into a graph. For example, each data sample can be regarded as a point on the graph. And then we can calculate the relation or distance between each pair of instances. Then, based on the distance, we can establish the edge to collect the different data points. Here in the graph, the colored points are labeled ones, where the white points are unlabeled data. Then what we want to do is just to propagate the color to the white points. So we can make very different assumptions. For example, we can assume that some data points very close to me will receive more information from my side. Then in this way, the label information can be propagated. So this category of approach have very nice mathematical foundation because each graph can be mapped to a matrix. Then we can use the mathematical matrix theory to do some analysis. But it also suffers from a weakness For example, if we have n number of samples, then we need to store an n square matrix. And then the analysis based on the n square matrix generally have the time order of n cubic or more. So it's very computational, expensive. And also, once we receive a new data, we need to insert the new data into the graph. Then it's very difficult to do that. So generally, this is a transactive setting of approach, not really do some inductive learning. So the fourth category approach is quite interesting. We have do a lot of work on this. This is a disagreement-based methods. In this kind of methods, they train multiple learners, and then to use the disagreement among the different learners to use unlabeled information. So this kind of approach does not assume to store all the data, and it does not assume a specific learner type. So it's generally scalable and very easy to be used in practice. So the very basic idea originally was designed for multi-view data. Here, multi-view data is each view is actually a feature set. For example, for the video data, it contains several sets of features. For example, we can use the image features or the text features, and each set of features corresponds to a view. So here is a very simple explanation about the seminal work named co-training. So given some labeled data and unlabeled data, now suppose we have two views. Each view corresponds to a feature set. For example, X view can be the image data set, image feature set. X2 view can be the text feature set. Then for the first step, from each feature set, we train a learner from the labeled data. Then the learner one only based on image feature. The learner two only based on the text feature. Then the learner one will pick some unlabeled data to give labels just based on image information. And the learner two will also pick some unlabeled data to give labels just based on text information. Then each newly labeled data will pass to the other learner. Thus, the both learners can be improved because they received some newly labeled data from the other learner. Then both learners can be improved and continue this process. So there are many theoretical studies about this approach. Although this approach is very simple, its performance is very nice and has been widely applied to practice. So people try to understand under which conditions the approach can work. So in the original seminal paper, Tom Mitchell and Bloom prove that given that the two views are conditional independent, then we can boost the performance of any initial weak predictor, for example, even the accuracy of 51% to actually high performance, such as 98 or 99% accuracy based on the use of unlabeled data. But unfortunately, in most real tasks, the conditional independence of the two views does not hold. So later on, we want to understand under which condition really enable the co-training process works. And people have given some results such as weak dependence, expansion of two views. And we have proved that actually, given that we can enable the two learners have difference, have large diversity, then they can give each up some other help to improve the performance. So this idea is very simple to understand because if you have two views, then each learner trained from different view, of course, they are different. Even if you do not have two views, if we can have some idea to make the two learners different, for example, by using different data samples or by using different parameter settings, they can be different, then they can still help each other. And finally, we have a sufficient and necessary condition and proved. And this results to us, two views are not really needed. So this kind of approach can also be applied to commonly encountered single feature set data. Then many approaches have been developed. For example, the tri-training approach tries to develop three learners. And by using some mechanism to enable each of the three learners are different, then these three learners can teach each other and the performance can be improved. And then finally, they can combine to give an ensemble prediction to give an even better performance. And recently, some researchers have extended this kind of idea to deep neural networks. And this methodology also work with deep neural networks. So this is a very quick overview of semi-space learning, but we can see semi-space learning still requires label data. Then what can we do if there are really very few label data? And the very few label data does not enable us to train a very accurate starting model. Then in this way, the S-cubic VM cannot work well because S-cubic VM requires some label data to do the starting work. And for the discriminant-based approach, we also need some label data to enable the initial 2 learner or 3 learners be not that poor. Then if the label data is very small, they still could not be launched. Then what can we do? Our answer is very simple. Now, if we have some knowledge, then even if we do not have good label data, we still can enable the learning process to continue. But the learning process could not be a pure machine learning. It should be pure machine learning together with logical reasoning. So it's a very long time, holy grail challenge of AI to have a unified framework to accommodate and enable machine learning and logical reasoning to work together. Because this is just the more motivation for us to have this conference. The motivation is very simple. Logical reasoning is easy to exploit knowledge. Machine learning easy to exploit the evidence or data. But most human decisions are based on knowledge plus evidence. But in the history of AI, we can see these 2 areas are almost separately developed. When logical reasoning and logical engineering are very hot, very few people paying attention to machine learning. But now, when machine learning is very hot and logical reasoning is less popular now. So the major difficulty lies in the very different representation. We all know that logical reasoning generally based on first-order logical representation, such as first-order predicates representation, based on the feature representation. So the feature representation, we can convert the data table to a propositional logic form, because each feature we can regard it as a true-false table. But these 2 different feature representation are still very hard for us to convert one form to another form. So we need to identify some other approach to combine these 2 different parts. So during past decades, there are many great efforts. Roughly speaking, we can categorize them into 2 parts to approach. The first typical approach, I give an example as a probabilistic logic programming. This is mostly logical reasoning researchers try to introduce some ideas from machine learning. For example, we can introduce probabilistic weighting into each logical clause. Then we can do probabilistic reasoning. This is a typical way. And another typical way is for machine learning researchers, which tries to introduce some idea from logical reasoning. For example, very famous statistical relational learning. Suppose we have the clause for any x. If x smokes, then entailment, the cancel x, then we can, in the graph, we can we can collect all the loads. If A has smokes and A has cancel, we add a edge. Then based on this way, we can regard it as initialization of the neural networks or initialization of the Bayesian networks. Then in the following, we can just apply neural networks training algorithm or Bayesian training algorithm based on the initialization. So roughly speaking, for the first category approach, it first introduced some machine learning, but then all the remaining tasks are almost fully accomplished by reasoning. So we call it heavy reasoning, light learning. For the second category, introduce some logical reasoning to machine learning in the first stage, in the starting stage. Then the following tasks are almost fully accomplished by machine learning. So we call it heavy learning and light reasoning. In particular, each representative approach, the final output of them may be some logical system. For example, in the first category, the result is some logical system. The logical system finally can do very rigorous reasoning. But in the future, when we have some new data, the learning to expand the logical system still meet some difficulty. For the second category approach, although the logical reasoning has been introduced, but the final output is still a machine learning, a black box model generally. And we can hardly do logical reasoning on this kind of machine learning model, then we lose the rigorous of the logic sense. So our ideal form is to have some model which can balance relatively more balanced to exploit logical reasoning and machine learning. And particularly, we hope that as a final learning result, it still enables us to do logical reasoning if we want to have some rigorous reasoning results, or we can do some machine learning if we can have some new data such that we can learn from some new experience. So recently, we proved a new proposal. It's named as abductive learning. So we know when we proposing the data or information, we have two typical ways. One, deductive, from general rule proceeds to a guaranteed specific conclusion, for example, theorem proving. And also we have inductive. So this is from specific observations and proceeds to a generalized conclusion that is likely but not certain in the light of accumulated evidence, for example, machine learning. And abductive, from the accurate definition, starts from incomplete observations, proceeds to the likeliest possible explanation for the set. But in our context, our basic idea is to inversely embed the deductive process into the inductive process. So this is a name we use, the abductive. It has some common sense with abductive in the logical reasoning community, and has also some other idea in the form. It's just the inversely embed the deductive into inductive. So let's look into the traditional supervised learning setting. We have some instances. This is the input part of the examples. We have the labels corresponds to the instance. This is the output parts. Then we combine the input parts and output parts to train the classifier. So this is what we do in supervised learning. Now in abductive learning, we assume that we are given a knowledge base. Here, we assume that the knowledge base contains many first-order logic clauses. And we have an initial classifier, and we have some instances. Now, we do not assume that we have the label information for the instances. We only have the input feature vectors. But in the later, I will discuss that when we have the label information, of course, we can use that. So with the instance, first, we can input the instance to the classifier. Then the classifier can give us some prediction. This is just a kind of a conjecture. Some predicted labels may be correct, some may be incorrect. So we call them the pseudo labels. Then we convert the pseudo labels into the form that the logical reasoning part can handle. For example, we can convert the labels into some pseudo groundings in the symbols such as A, lective B, not C, and so on. Then what we want to do is to do logical reasoning to see whether pseudo groundings are consistent with the logic base. If it's consistent, then we have already got the result. If it's not consistent, then we may identify several places. For these places, once we do some revision, the consistency will be improved. Then we identify the place where the revision can improve the consistency to the most. So we call it to just optimize the minimal inconsistency. That means we want to minimize the inconsistency. Now suppose once we found that once we revise lective C to C, then the inconsistency will be dropped significantly. Then we do the revision. Then we convert the pseudo groundings, revised pseudo groundings to the abduced labels. Then the abduced labels are together with the instance to train a new classifier. Then the classifier will use to replace the original classifier as the process continue. So we can see the left-hand side is the machine learning parts. The right-hand side is logical reasoning. And these two parts will be continue used in the loop. First machine learning, then logical reasoning, then machine learning and logical reasoning, until the classifier, which the pseudo groundings generated from the classifier are consistent with logic base, or the classifier does not improve in several rounds, then we stop. So finally, we can have a classifier, and we can also have logic base. Then once we want to do reasoning, we can use the logic base. Once we have some new data, want to learn from the new data, we can try to refine the classifier. So here we have some remarks. First, in my previous navigation, I mentioned that we do not assume they are labels, but actually, if we really have some ground truth labels, this label can be used. For example, the labels can be used to generate more reliable pseudo labels, and also the trend classifier can be improved with ground truth labels. Then from this way, this approach can be regarded as a kind of weakly supervised learning. The supervision information can be even as weak as no label information, because now the supervision is from the knowledge base together with the labels. Then even if we do not have labels, once we have knowledge base, we still have sufficient supervision information to enable us to train a good classifier. Another remark is, you may be curious, where can we have the classifier? Now, in the deep learning age, we all know there are many pre-trained models. Then if we have pre-trained models, we can do the initial classifier. Or if we do not run deep learning, but if we do some transfer learning, we can transfer some model from other related domains to be used as an initial classifier. And even if we do not have the deep learning pre-trained model or transfer learning transfer model, we still can do some very simple way. For example, we can run Keynote label classification, or even do a very simple clustering. Though this performance can be very poor, here it does not matter because we only need to have the first step to be started. Once it has been started, if the initial model is very poor, if we have very strong knowledge, then the knowledge can help us to improve the model. So the key is, even if the initial classifier or initial data is very poor, once we have strong knowledge, then the knowledge can help us to get a very strong machine learning model. And then currently the knowledge can only be manually written, and we assume they are first order logical clauses. But if we know the knowledge base is incomplete or inaccurate, then the abductive learning approach can be also regarded as a mechanism to do the knowledge refinement. For example, now we do not constrain the revision to be only on pseudo groundings. We can also identify some parts in the knowledge base to enable them to be revisable. Then in this way, the optimization becomes more difficult, but this give us a possibility to do knowledge refinement. So overall, if we have some good knowledge, then we can train good model. If we can have good data, we can train good model and also can do knowledge refinement. If both are good, then we can do even stronger things. If both are very poor, then this is not a task that we should try to solve. So these are very general framework. Then there are many places require some installation. For example, how to do the learning part, how to do the reasoning, how to do the conversion. Different implementation leads to different models. Here I show you a very simple illustrative realization. Here the task is in this way. Now the first string is a positive string. The second string is a negative string. Then based on this training data, we want to predict whether the third very long string is positive or negative. Now this is a kind of problem. We need to not only recognize what the symbols represent, also we need to discover what is the unknown operation behind the samples. Here, the operation is XNOR behind the samples. Now, the first data set we generate is a synthetic one. The left-hand side, we can see the training data. There are 5 bits. Each bit corresponds to an image. For example, 0 plus 0 equals to 0. This is a positive example. 0 plus 1 equals to 1, also positive. 1 plus 0 equals to 0, this is negative. Then based on the training from these 5-bit images, we want to make a prediction on the very long string, such as in the right-hand side. And also the second task is even more challenging. Now the images are randomly generated, and even the meaning could not be very easily read by human beings. So we still training by the 5-bit image, then to make prediction on the very long string. So here are our realization. Now, because the machine learning part involves the recognition of images, we use convolutional neural network. Because CNN has open source data code, then it's very easy to be used. And for the logical reasoning part, we use the Abductive logical program. It also has open source code. And the most challenging part is how to do the optimization. Now, because we want to minimize the inconsistency between the pseudo groundings as well as knowledge base, they are based on the symbolic optimization. So we can hardly apply the very popular gradient approach, such as stochastic gradient optimization, could not be used here because we can hardly calculate the derivative of the symbols. Here, we use a set of tool developed in my own team. It's called derivative-free optimization. This is a kind of a tool which do optimization does not resort to the calculation of gradient. Then now we also have some open source code for that. Then this pinning of these three sets of open source code give the implementation of this approach. So we can see the results. So here, the red curve corresponds to the abductive learning result, and the blue curve and the purple curve corresponds to implementation of some deep neural networks. So we can see the performance of abductive learning by using machine learning together with logical reasoning is much better than purely deep learning, because the deep learning approach does not exploit the knowledge base, where our abductive learning exploit knowledge base together with machine learning. And in particular, we can see there are two lines, horizontal lines. The line corresponds to 0.5 is random guess. The line slightly better than 0.7 is the performance of human beings. So we can see in this very special case, by using machine learning together with logical reasoning, the performance is even better than human beings. So this is a very synthetic task. Now I will briefly introduce a very preliminary application of this approach. This is a joint study with a court, with some judge. This is a law enforcement application about theft judicial sentencing. So in China, in order to maintain the justice or fairness of the law enforcement, the high courts in China often examine the quality of sentences made by local courts. Previously, this is by manual examination. So it's tremendous human resource required, very time consuming. Now, what we want to develop intelligent assistant is to check the judicial documents. It's very difficult for me to translate the judicial documents into English. So I just give you some brief idea. The judicial documents include three parts. The first part contains some general information such as title and case ID, basic information. It's not useful for our task. The second part is the main body. It's very important. It involves facts of the crime, investigation, the trial results, applicable regulation, and so on. The third part is the output, is the sentencing results. So for a human judge, when they do the examination, they just read the judicial documents and see the output is whether correct or not. So we can see the output, the term of imprisonment in months as a kind of a ground truth. But for the computer programs, we need to divide it into two parts. For the first part, we need to identify, to recognize the judgment elements, such as whether they are burglary or pickpockets and so on. And then based on the judgment elements, we will apply the law regulations to get the term of imprisonment. So we can see the first step is actually a natural language processing task. We have input the judicial documents. The output is the judgment elements in symbols. The second part is a typical logical reasoning. We have the elements, then we apply the reasoning based on the law regulations, and then we get the output. But actually, these two parts, none of them are easy. For example, for the first part, though there are many cases, millions of cases, but very few have been labeled by the judge. So these are very typically weakly supervised learning setting. And even for the labeled judgment elements, they are insufficient, incomplete, and inaccurate because the label task is very difficult. For example, here I just show one case. In this case, the burglary is an important element, but it has not been labeled. And it's even very difficult to be recognized. If you do some Chinese natural language understanding, so there are some words such as crack window and kick the door. But crack window and kick the door does not mean burglary. There are also some possibility of going to some vehicle for theft. These are different cases. So this kind of recognition is very difficult. Even when we apply some NLP state-of-the-art technique, its accuracy is still have some difference with the requirements of the law enforcement applications. And for the second part, even when we have the judgment elements, it's still not easy because the logical reasoning is not that simple. Some judge have some flexibility. For example, for some case, under some conditions, they can have lighter punishment. But how lighter it is, reduce 3 months or reduce 5 months is very different for different judge. So this is also difficult. So each step are not that accurate. Then if we have one step to help another, maybe we can even do better. For example, if the elements are not that accurate, then the application of the law reasoning, maybe the result is not that accurate. Then if we know the reasoning result is not accurate, then this can give us guidance. We need to revise some original recognition. Then in this way, the both parts can help each other to improve. So this naturally fall map to the abductive learning framework. Now, let me show you one very simple sample. Now we have one judicial document. We give the classifier and need to do some initial recognition. The recognition is wrong. It predicts the pseudo groundings, no burglary, no pickpocket. Then we put the result together with knowledge base to do the reasoning. Here is the detail of the reasoning. Based on this information, the no burglary, no pickpocket, and the money involved is 450. Based on this information, based on the reasoning, we can get a predicted result is 6 months for the punishment. But the ground truth is 7, so there are big difference. So this difference gives us guidance that some elements need to be corrected. Then we identify the rules, the knowledge which has been filed in this reasoning. Then there are one rule which predicts that the term smaller than 3 years, but its involved money should be 1,000, between 1,000 or 30,000. But for this case, it only involves 450. Then this condition does not fail. Then the other two conditions, burglary or pickpocket, at least one must be occurred. So we have the two possibility. One is burglary with no pickpocket, or one is no burglary but pickpocket. Based on each of them, we have the optimized results, 0.8, 6.8, or 6.1. Then to minimize the inconsistency, we'll select the 6.8. Then we get the result that the burglary should be changed. No burglary should be changed to burglary. Then after the abduced labels to convert to the original, then we retrain the classifier. Then the classifier can be improved in this way. So this is some results. We have several thousands of cases manually labeled by the human judge. So the first table shows element recognition performance. Here, the number such as 10 or 15 explains how many percentile of the data are labeled to this approach. For example, the ABL 10 means the abductive learning approach used just 10% of data as labeled data, and all the other data is unlabeled data. BERT 100 means for the BERT approach, which is very popular, but it uses 100% of all the data for labeled data. So we can see the abductive learning approach, the performance is superior on the sentencing elements prediction. When using 10% of labeled data, it's even better than BERT using 50% data, because the BERT could not use knowledge. It only use the data to learn the model. And the gain from utilizing knowledge and unlabeled data is larger when there are less labeled data. Also, for the final sentencing performance, we can see that by using the knowledge base, the performance is much better than the other approach, which are only user data. On the other hand, the abductive learning approach, because we use logical reasoning, we also generate some sentencing rules in the symbolic logic way. For example, we now see this kind of cases, a base sentence is 0.6 months plus 6. And if a burglary, then the base punishment plus 6%. If the get some forgiveness from the victim, then from the base punishment get 50% reducement. So this kind of sentencing rules are understandable and easy to examine and verify, and offering aids to human judge. So this is a very simple summary. Now, learning with unlabeled data is very important, but self-training is too live. And there are well-established approach. If we have human in the loop, we can do active learning. If we have light labeled data, we can do semispace learning. If we do not have human in the loop or do not have light labeled data, we can run abductive learning if we have knowledge base. And this is a way towards a unified framework for machine learning plus logical reasoning, but it's just a start and many things to do. On the other hand, as I have shown you, the machine learning is at the left-hand side and the logical reasoning is the right-hand side. If we have a turnaround of the graph, then we can see the top side is logical reasoning. The bottom side is machine learning. This offers a possibility for us to understanding calculation and perception, because perception corresponds to machine learning and the calculation maybe corresponds to logical reasoning. And these two parts should help each other in a loop and continuously. That's all for my talk. This is a joint work with my students, Wangzhou Dai and Yuxuan Huang and many other colleagues. And recently we have a chapter to summarize the whole work, but if you have interest to semi-supervised learning and active learning, this is another brief overview. That's all, thank you.